Hello everyone, welcome back to my channel. I am Dr. Saravanan from the Department of Physics, Sikkim Manipal Institute of Technology. I am excited to bring you to this new lecture series on quantum mechanics 1. As we know, quantum mechanics is one of the exciting and interesting branch of physics. It describes the behavior of energy and matter at the smallest scale. Unlike classical mechanics, it introduces new concepts like superposition, wave-particle duality, uncertainties of physical quantities, and quantum tunneling, and many more things, which challenges our intuition, but at the same time, it deepens our understanding of the physical universe around us. So it paved the way for modern science and has led us to the many technological applications such as semiconductor, laser, quantum computing, and etc. So this lecture series is carefully designed for students preparing for NET, GATE, and SET and many master level exams. In this lecture series, we'll focus on building a strong foundations in quantum mechanics by solving problems. I personally believe solving problems is not only helpful for understanding the basics well, but it develops the confidence to apply them effectively. So in this lecture series, I will not discuss the list of experiments that illustrate the failures of classical mechanics and birth of quantum mechanics. We'll directly dive into the mathematical formalism needed to study the quantum mechanics, and then we'll study the postulates of quantum mechanics, and we'll derive Schrödinger time independent and dependent equations, and we'll apply them to study the some of the basic problems like particle in an infinite potential, finite potential, will hydrogen atom, harmonic oscillator, treatment, analytical and operator method, and finally we'll study the orbital angular momentum and spin angular momentum, and we will finish. So at the end of this course, you will have a strong clarity on the fundamentals that are essential not only for exam but for the understanding of advanced physics. So stay tuned. Let's embark on this fascinating journey of exciting world of quantum mechanics. Please subscribe and click the bell icon so you won't miss any lecture from this series. Let's get started. As a first lecture of this series, under the heading of Mathematical Formalism for Quantum Mechanics, today we are going to discuss about the linear vector space. At first, I will be discussing about the state vector representation of quantum mechanical system in linear vector space, and then the idea of Hilbert space and some properties of Hilbert space such as scalar product of state vector and idea of Dirac notations and the dimension and basis of vector space and examples of linear vector space and inequalities such as Schwarz and triangle inequalities, and then the ideas of orthogonal and orthonormality of state vectors will be discussed. Schrödinger equation in quantum mechanics. Plays the same role as that of Newton's equation in classical mechanics. We know the Newton's equation of motion is F is equal to ma. It's a second order differential equation. Depending on the nature of force applied on the system, it will be either linear or non-linear differential equation. So accounting constraint force of a classical system is very difficult using this approach. So the more refined version of studying classical system by accounting all the constraint force is through the Hamiltonian dynamics, which involves framing Hamilton's equations of motion, which are nothing but the two first order time derived generalized position and generalized momentum equation. So the first equation is the time derivative of generalized position, which is nothing but the derivative Hamiltonian with respect to the generalized momenta, and the time derivative of momentum, generalized momentum, is given by negative of the derivative Hamiltonian with respect to position q. So once if you solve this two equation, you will get position and momentum as a function of time for each degrees of freedom. For each degrees of freedom, you can write an equation of motion once if you know all the generalized position and momenta of the classical system. But if you take the quantum system, you cannot simultaneously find these two quantity, position and momentum, you cannot find simultaneously. So this concept is no longer useful in quantum mechanics. And the Schrödinger equation is a second order linear differential equation. Mark this word linear, it has a very useful applications. So let me give first an example of generalized general form of linear differential equation, which is d squared y by dx squared plus p times dy by dx plus q times y is equal to r. This is a generalized form of linear differential equation, second order linear differential equation with constant coefficients. Here p and q are constants and r is a driving function which is a function of x, which can be in general e raised to x, sin x, cos x, etc., etc. Okay, so these are the linear differential equation generalized form. How the nonlinear equation appears? Let me give an example. D squared y by dx squared plus p time dy by dx plus q time y squared. This is one example. Another example can be d squared y by dx squared plus p time dy by dx. You can see these two are nonlinear differential equation. Either the power of dependent variable, here y squared, or its derivative, its power also can be, if it is more than 1, then this equation is called nonlinear differential equation. So system dynamics will be very chaotic and it will have a sensitive dependence for initial conditions. Whereas for linear differential equation, it has some special property. So if you consider this harmonic oscillator equation is also linear, one of linear differential equation. So this is harmonic oscillator equation. We know it's a solution. Standard solutions are y. There are two independent solutions. One will be a time cos omega x. Another one can be b time sin omega x. And these two equations will independently satisfy this equation number 4. These two solutions, this equation also, this solution also will satisfy, and this solution also will satisfy this equation. And in addition to that, any linear combination of this equation, let's say I am taking y, some c time y1 and d time y2, and this solution also will satisfy this equation. So that is the special property it has. So any linear combination is also a solution of a linear differential equation. Okay. So once if you solve this Schrödinger equation, what one would get? You will get the state vector of the system. This is, we used to call it as wave function of the system. It's just a mathematical function. Psi itself, wave function. So what is this angular bracket? These angular brackets are called Dirac's notation. We will discuss this in detail later. So consider this is a state vector of the system, or it is also called wave function. It's just a mathematical function. Psi itself doesn't have any physical meaning. It's also one element of the Hilbert space. It's a vector. So we have a space called Hilbert space, mathematical space. It's an one element of the psi is just one vector from this space. Okay. So so how to find the physical quantities of the quantum mechanical system? Once if you know this, these contain. Once if you find the after solving Schrödinger equation, if you find the wave function, then you know everything about the system. How to find the physical quantities? Suppose you have the state function or wave function of the system. Now you want the momentum. For that you have to take momentum operator, operate on the state function. If you do so, you will get momentum as the eigenvalues of the system. And if you want kinetic energy, then take the kinetic energy operator, operate it on, then you will get kinetic energy as the eigenvalues. So if you want position, then take the position operator, operate it on the state function or wave function, then you will get position of the particle with some certain probability. So you can see you cannot compare wave function or state function as with the position of the system as like in Newtonian mechanics. This comparison has no meaning. Okay, the dimension will be completely different. If you there is no meaning of comparison, just a mathematical function. So what is the meaning of psi? As per Bohr's probabilistic interpretation, mod psi squared is called the probability amplitude. So if you want the probability of finding the system over some volume, let's say V dV, some infinitesimal volume dV, then you have to multiply mod psi squared with this volume. This will give the probability of finding the particle within this volume. So as I told that to understand how this state vector can be used for obtaining the system parameter, one has to understand the Hilbert space in detail. Let's discuss the Hilbert space. So Hilbert space is a mathematical space. It has the properties of linear vector space. It's a linear vector space with defined scalar product. With a defined scalar product properties. So space that has the scalar product or some length associated with it is also called metric space. Okay, let's discuss the properties of first linear vector space. So I'm denoting linear vector space as LVS. Okay, so linear vector space consists of two sets of elements. Okay, what are those elements? These elements are vectors and scalars. So it has some set of vectors which I am denoting it as ket psi. So this symbol I will be calling it as ket psi, phi, ket chi, and so on. And it has a list of some set of scalars which I will be denoting it as alphabet A, B, C, D, and so on. Okay. And in addition to these two elements, it also some mathematical rules. What are those rules? We have two sets of rules. A rule for vector addition and rule for scalar multiplication. We'll see what is the properties of vector addition and scalar multiplication. Vector addition has the following properties. So, if you take a vector from the linear vector space psi and take some other vector phi from the same linear vector space, if you add these two vectors, then you will get the resultant vector, let's say chi, which I am denoting it as chi. Again, this vector will also from the same linear vector space. So adding any two vector will result some other vector. Again, the resultant vector also from the same linear vector space. And the order of addition of two vectors is immatter, meaning that if we want to add psi with phi, either you can add in this way or at first you can put phi and then psi. The result will be same in both case, and this vector will be lying in the same linear vector space. Next, so this is called, this property 2 is called commutativity. Vector addition is commutative. And association, when you add three vectors psi, phi and chi, what you can do, at first you can add psi and phi, the resultant vector can be added with chi. If you do that, or you can do other way also. At first you can add phi with chi, the resultant vector can be again added with psi. In both case you will get the result as some other vector. Let's take a delta. In both case answer will be same. So the association of this is called associativity property, means the association of two vectors when you add three vectors is immatter. Okay. Associativity, vector addition has the associativity property. And there exists a special vector called null vector, which I am denoting it as O, such that when you add this null vector with any vector from the linear vector space, answer will be same. It doesn't make any change. Okay. And the fifth property, there exists a symmetric vector for each vector from the linear vector space. Suppose if you take a vector from the linear vector space, for this vector there exists a symmetric vector, which I am denoting it as minus of that vector, such that when you add the vector and then symmetric vector, you will get null vector as your result. Okay, these are the properties of vector addition in linear vector space. Now let's list out the properties of scalar multiplication. So if you take a vector from the linear vector space, when you multiply a scalar with this vector, then you will get some other vector, let's say psi dash. Again this vector will also belongs to the same linear vector space. This multiplication of scalar with a vector produces a new vector. Okay, and any linear superposition of two vector will give you a new vector that will belongs to the same linear vector space. Linear superposition of two vector will result a new vector from the same space. Okay, so this commutativity means when you multiply a scalar with the addition of two vector, this is equivalent to multiplying the scalar individually and then add them. In both cases result will be same, meaning that the distributive scalar multiplication is distributive with respect to vector addition. That is the meaning. Next, so the scalar multiplication has the associativity property, meaning that if you want to multiply a scalar with the vector and then result you are again when you multiply with some other scalar, what you can do, you can at first you can multiply these two scalar and the result can be multiplied with the vector. The result will be same. This scalar multiplication is associativity. Is associative. Okay, and there exists special vector called unit vector. No, special scalar called unit scalars 1 and 0, such that when you multiply the unit scalar and any vector in the Hilbert space or linear vector space, you will get the same vector. So multiplication of unit vector and any vector will not make any changes. Whereas if you multiply the zero scalar with any vector from the linear vector space, you will get a null vector. So these are the properties of scalar multiplication of linear vector space. So linear vector space, as I told, is the Hilbert space is a linear vector space. The Hilbert space contains all the properties of linear vector space. In addition to that, it has the special property called scalar product. So I should make it as B, I think. B. Okay. Hilbert space is a inner product space or metric space. Okay. Before discussing about the inner product properties or scalar product properties of Hilbert space, let's discuss what is Dirac notation and what is its use. We know a vector, let's say I am denoting it as A. This vector I can represent in Cartesian coordinate system, or I can use cylindrical coordinate system, or I can use spherical polar coordinate system. Whatever coordinate system you use, the idea of vector or the norm of this vector or its length is not going to change. Length is independent of coordinate representation, or the idea of vector is independent of coordinate system. So likewise, I told the state of the system we represent in terms of state vector or ket vector, which belongs to the infinite dimensional Hilbert space. It's also a vector. So I can expand this mathematical function. This psi is nothing but mathematical function in different bases. Okay, so I can use position base, I can use momentum base, so I can use any base that I wish. Okay, so but the idea of the system, I have a quantum system, I am representing it by some state vector. The notion of vector remains same. Whatever coordinates system you choose to represent it, that is your wish, but the idea of state vector is same everywhere. So what Dirac thought, we have to create some abstract notation which free the idea of vector from the coordinate representation. So that's why he used the ket vector. Ket vector stands for, we are picking a vector that is from actual space. If you take Hilbert space, this vector is coming from, ket vectors are coming from Hilbert space, and he also used bra vector that is coming from dual of Hilbert space. So if we denote a vector by a bra sign with bra sign, that is coming from dual space. Here, since space is Hilbert space, it's coming from dual of Hilbert space. And he also used another symbol called bracket notation. This stands for scalar product. Scalar product of two vectors psi and phi. We know the what is scalar product. It's a process of associating a scalar with the two vectors. So we know in real Cartesian Euclidean space, what is the meaning of doing scalar product? I take two vector and multiply component wise. At the end you will get some constant. I am representing it by C. Okay, similarly, here you are doing scalar product using Dirac notation. That is the only change. If you do this, so you have to write this psi vector from the Hilbert space. Okay, from the Hilbert space, and the bra vector, that you have to take it from dual of Hilbert space. And this, why this distinction is coming? Okay, for this case you take in for real scalar product, when you do in real Euclidean space, you don't you won't often discuss whether I am taking the vectors from the dual space or the actual space itself. That distinction you won't make in real Euclidean space. Whereas when you come to the complex function space, it matter, because these two are not equal. Phi, scalar product of phi with psi is not equal to scalar product of psi with phi. It is not commutative. Scalar product or inner product is not commutative. That's why you have to assume that when you do scalar product, the first vector should come from the dual of the space. So whenever you have some complex function here, if you have a complex function of phi, you know it is coming from Hilbert space. But when you put it here to do scalar product, you have to, now you have to write it as a bra vector. So in that case you have to take complex conjugate of this and then do the scalar product, then you will get the proper answer. Otherwise, if you don't take complex conjugate, then there will be a problem. We often used to represent the vector in terms of its components by a matrix notation. So when you do this scalar product in using matrix symbol, then it is uh, very much sensible. Means it makes good sense. Suppose you have uh, two vector phi and psi. Okay, you know its components. You know psi vectors are, so psi vector in matrix notation, ket vector in matrix notation, we often used to represent by a column matrix. Okay, 2 3 I 4. Okay, and if you have phi vector, again, so it's a ket phi. Remember, this is a ket phi, so I have to represent it by a column matrix which has the elements I 1 2. Okay, Now when you take the scalar product, you have to put bra phi instead of ket phi. You have to ket phi is given, so you have to put bra phi. And how to find the bra phi? Just take the complex conjugate. How to do the complex conjugate? No, you have to make the all the elements as complex conjugate and do the transpose. The transpose of column matrix is row matrix. So here it is minus I 1 2 and then multiply with the column matrix. Now you can see this column matrix become row matrix, and here you have to put this one. So when you do this, you will get a single number minus 2i plus 3i plus 8. So it's some complex number. So you can see in matrix representation, bra vectors are row matrix, single element row matrix, and ket vectors are column matrix. Okay, so when you take a scalar product, you will get a single number. Now, so what happens when you take a scalar product of vector with its of same vector? You are taking scalar product of a vector with itself. So if you do that, you will get some scalar quantity, but it should be strictly positive. It should be greater than or equal to 0. It will not take a negative value, because this is associated with length square of a vector. When you do this, you will get a length square of the length of vector, and that has to be always positive. You cannot, length can't be negative. Okay, so this is strictly a positive quantity. Scalar product of a vector with itself is a strictly positive quantity, and when this equality is holds, whenever you take scalar product of 0 vector with itself, then this equality holds. Otherwise, it is strictly a positive quantity. Okay. Now, let's discuss what is uh, dimension and basis of vector space. So one more thing, this quantity here, taking scalar product of vector with itself, is called norm. This is also called norm of the vector. And if you want the length of the vector, you have to take square root of norm, which is this one. This will give the length of the vector. Okay. Now we'll come to dimension. To understand the concept of dimension of vector space, one has to understand the concept of linearly independent and linearly dependent vector set. Okay, suppose I have a collection of vectors which belongs to the Hilbert space. So when I can say these vectors are linearly independent and linearly dependent. So using these vectors, what you have to do, you have to frame an equation of this kind, which I am representing it by some shorthand. I have n such vectors. Okay, this I runs from 1 to n. Okay, n such vector, and you have to frame such equation. And if it turns out that the solutions of these equations are trivial equations, if all the ai's are 0, then this vector set is called linearly independent set of vectors. So it's a group properties. So it tells that linear independence of the state vector. So often our state vectors are used to be the function. So for functional space, so vectors will be a mathematical function. Suppose let's say you have two-dimensional functional space. your f1 is cos x and f2 is sin x. Okay, now how you can say this vector are linearly independent set of vectors? So in that case, what one can do, take the Wronskian of this function. So you have to find this, put f1, f2, f1 dash, f2 dash, sorry, single derivative of the function with respect to independent. If the ranks, this is called Wronskian determinant of this. So you have to make a matrix and find the determinant, and if you do that, this is called Wronskian. If Wronskian turns out to be 0, then these vectors are linearly dependent. If Wronskian is not equal to 0, then this vector set will be a linearly independent set of vectors. Okay, this is why that whenever we say we know the matrix properties. If you have a square matrix, if you somehow represent one row or one column is linearly dependent with other column, means if you somehow express row 1, row 2, if you know that R2 is equal to some 2 times R1, if they are linearly dependent, you will get the determinant as 0. If this is matrix, then if determinant of this matrix will be 0. So this become linearly dependent. So we know the vectors we usually express as a by components as a matrix. Okay, so when you express if its components are linearly dependent, the vector set also will be linearly dependent, and the determinant Wronskian should be equal to 0. This is nothing but Wronskian determinant of the matrix. If it turns out to 0, then this vector set will be a linearly dependent set. Okay, now what is the dimension of the vector space? So dimension of the vector space is the maximum number of linearly independent set of vector the space can have. Okay, the dimension of the vector space, the dimension of a vector space is the maximum number of linearly independent set of vectors the space can have. Okay, so this is called the dimension. Next we will see what is basis. So what is the dimension of Euclidean space? Dimension of Euclidean space is 3, because the linearly independent set of vectors are only I, j, k in all 3 directions. Okay, this by any means you cannot express I vector in terms of j vector, or by any means you cannot express I vector in terms of k vector. It's not possible. They are linearly independent set of vectors. So that's why it's a dimension. So number of linearly independent set of vectors for Euclidean system, coordinate system is 3. That's why its dimension is 3. Okay. What is basis? Basis vectors are the linearly independent set of vectors. So it's a group of linearly independent set of vectors are called basis vector, which we used to represent it by this symbol. So if the dimension of the number of such elements will be equal to the dimension of the system. Suppose if the space has the dimension of n, this I will run from 1 to n. So this is called basis. This is ijk. Basis for Euclidean space is ijk, and the number of bases is equal to the dimension of the basis. That's all. So next we will discuss some examples of linear vector space. So examples of linear vector space, if you take a set of numbers in one dimension, this itself satisfy all the properties of linear vector space, and we can define unit vector, null vector, symmetric vector, everything. So set of numbers in 1D, set of real numbers, set of real numbers in 1D. So which we used to represent it by this symbol R1. And as a ordered set of numbers in 2D is also another example of linear vector space, which we used to represent it by R2 and R3, set of numbers in real Euclidean space. This is Euclidean space. So ordinary Euclidean space we used to represent it by R3. Okay, so we can have similarly an n-dimensional set of ordered n-tuples, we used to call n-tuples, and that we used to represent it by r raised to n. This is also qualified, we say, as linear vector space. It's a vector space, mathematical space. Okay, so and if you take the solutions of differential equation, if you take second order differential equation of a harmonic oscillator, dt squared plus omega squared into dx squared dx squared, one minute, take a harmonic oscillator equation, d squared y by dx squared plus omega squared into x is equal to 0. Its solutions we know, y1 is equal to a sin x and y2 is equal to a cos x, and any linear combination of this equation will be also any solution of this equation. So this is one solution, this is another solution. Make any linear combination of these two solutions, again that equation will satisfy this equation. So it's also qualified to be say as linear vector space. Okay, so functional space. Next, a set of vectors can form a linear vector space. Set of matrices can form linear vector space. Take some 2D matrix 2 1 3 4 and add with some other 2D matrix 3 1 2 5. Then the resultant vector will again be a 2 cross 2 matrix. So you can see that belongs to some group of vectors, matrix vectors that you have. Okay, all these properties, as I told earlier, the properties of linear vector space and inner product, idea of inner product, everything will satisfy the matrix space, also will satisfy those properties. So the set of matrices can form a vector space. These are some examples. So one of the important properties of Hilbert space is the Schwarz inequality. Yes, so what it says is that if you take any two vectors from the Hilbert space, phi and psi, it satisfies this following inequality: the mod square of scalar product of psi with phi is always less than or equal to the scalar product of psi with psi and multiplied with the scalar product of phi with phi. So this ensures that the linear independence of the state vectors. If suppose if I express psi some alpha times phi, means if they are linearly dependent, I cannot write this equation. If they are linearly suppose dependent, then I can write such equation. And if you substitute here psi in place of phi, so phi in place of psi as alpha times phi, so what one would get, this will be alpha times phi and phi all squared less than or equal to, so alpha times phi and alpha times phi multiplied alpha times phi, this one, and what this will give you, mod alpha squared phi with phi, this quantity, this one, and here again we will get mod alpha squared scalar product of phi with phi into scalar product of phi with phi. So here you can see this alpha square will get cancelled, and mod scalar product of phi with phi, and it's a square, it become an equality. Here you can see. So if vectors in the Hilbert space are linearly dependent, then this equality no longer holds. This inequality became an equality. That's what's showed here. Let's discuss two more properties of straight vectors from the Hilbert space. If I take two vectors ket phi and ket psi from the Hilbert space, and if it turns out that the scalar product between these two vectors, if it turns out to be 0, then these vectors are called orthogonal set of vectors. In addition to this, if I have some collection of vectors, okay, I runs from 1 to let's say some n. Okay, now if it turns out that the inner product of any two vectors from this set Kronecker delta, which means that Kronecker delta will take 1 if I is equal to j. If I is not equal to j, it will take I is not equal to j, it will take 0. So if the vector set satisfy this property, then it is called orthonormal set of vectors. Orthonormal set of vectors. If a vector is normalized vector, then the inner product of vector with itself will be equal to 1. Okay, and also all the basis vector set should be orthonormal set of vectors. Basis set should be orthonormal set of vectors. So that's all. In my next lecture, we will solve some problems from this series, from these topics that we discussed. Thank you. We also have another kind of inequality in Hilbert space is called triangle inequality. This is much like as the Euclidean space triangle inequality. So if you have a triangle of this kind, one side is A, other side is B, and third side is A plus B, and if you take the length of the third side, which is mod A plus B, is always less than or equal to length of side A plus length of side B. This is triangle inequality. In much the same way, in the elements in the Hilbert space or vectors in the Hilbert space also satisfy such kind of triangle inequality. If we take two such vector elements phi and psi, they satisfy the triangle inequality, which I am representing as length of third side is inner product of psi plus phi with psi plus phi is always less than or equal to the square root of the inner product of psi with psi plus square root of the inner product of phi with phi. So this ensures that the linear independent of the state vector that we consider here. This tells that these two vectors are linearly independent. Suppose if this inequality breaks, suppose if this breaks mean what? I can somehow express psi some constant times phi. Means if they two become linearly dependent, what one can do, substitute this here. I assume that alpha is real and positive quantity, so wherever psi comes, write alpha times phi. In the square root, psi is alpha times phi plus phi, alpha times phi plus phi only less than root of alpha times phi plus phi. Okay, now you can see here phi is, you can take phi commonly out from this expression and it becomes alpha times alpha plus 1 times phi here. Alpha plus 1 times 5 here. So it's less than or equal to, here you can take alpha and then square root of scalar product of phi with phi. So here you can see one alpha plus 1 can be taken commonly out. So there will be a square root under square root square, and under square root it will become alpha plus 1, and then this becomes alpha times alpha, square root of inner product of phi with phi is less than alpha plus 1 times square root of inner product of phi with phi. Now you see it becomes equality. It's now both left hand side and right hand side is now equal. It's not unequal. Both are equal. So you can see when vectors are linearly dependent, the triangle inequality becomes an equality. Let's discuss two more properties of straight vectors from the Hilbert space. If I take two vectors ket phi and ket psi from the Hilbert space, and if it turns out that the scalar product between these two vectors, if it turns out to be 0, then these vectors are called orthogonal set of vectors. In addition to this, if I have some collection of vectors, okay, I runs from 1 to let's say some n. Okay, now if it turns out that the inner product of any two vectors from this set Kronecker delta, which means that Kronecker delta will take 1 if I is equal to j. If I is not equal to j, it will take I is not equal to j, it will take 0. So if the vector set satisfy this property, then it is called orthonormal set of vectors. Orthonormal set of vectors. If a vector is normalized vector, then the inner product of vector with itself will be equal to 1. Okay, and also all the basis vector set should be orthonormal set of vectors. Basis set should be orthonormal set of vectors. So that's all. In my next lecture, we will solve some problems from this series, from these topics that we discussed. Thank you.